Oh, looks like it's time. Welcome back, everyone. I think I was just sort of staring off into space, so I'm not too much over time. Well, for the announcements today, it's all kind of spread out everywhere, but let's go through them anyways. It just doesn't seem right to start class otherwise. We're made a start on this section right here, 4.6, but we did do a lot of work right before example one. So a lot of stuff happened right before that example. Or I think we might be on example two. Well, we'll get into that. And in the very next section, we're going to start looking into what we mean by integration, looking at areas under curves. We'll look at areas as they relate to practical problems. Pathogenesis is a really interesting application in that section, but I'm going to be looking into the application of distances on the actual lecture notes. It's a little bit easier, I think, to actually see the concepts come together there. Also, probably the bigger things we're wondering about are the upcoming exam 3. Like we mentioned before, it's just going to be over these 4 sections right here. So that means 4.6 is going beyond that exam. This is going to be final exam material at this point. But quiz 10 is now super pivotal. I believe that section 4.4 in a calculus class is probably one of the most important sections because it gives you a really strong idea of one of the major powerful tools of calculus, which is optimization. But at the same time, optimization is hard. I just have to admit it. There's no other way around it. There's a lot of math to do, lots of things to think about. And so the question that I'm going to ask here in section 4.4, I'm not going to try to get too wild on that. It's going to be pretty well contained. And the hint is, if you can solve quiz 10, then you're in pretty good shape for that question there in section 4.4. So the quiz due date is April 17th, which is the standard due date we expect, a 1-week turnaround. If you get that into me before the day of the exam, I will be able to grade it and send you back feedback. So you'll know just about how you're doing on section 4.4. Not saying try to solve it fast as possible and not be able to do your best effort on it. So if you need additional time to solve it, then definitely take that time. And if you send this quiz to me on Monday, the day of the exam, it can be kind of tough for me to grade it, but I'll make every effort to make that happen. I'll grade them as they come in, as a first comes, first served basis, essentially. And I would say probably just for a good benchmark, if you're studying the exam on Monday, again, the quiz 10 is a really great way to study for the exam. Then I should be able to grade that and get it back to you. I don't know why I pulled up the clock, but here it is. If you get to me before noon on Monday, I'd say I'd have a really good shot at getting it graded and returned back to you. Aside from that, these are the typical materials you'd expect on the exam. Don't forget, you will need a calculator, much like on the last exam. Not a lot of questions directly are attacked by a calculator, but I think section 4.4 is almost a guarantee you would need one for that section's problem. Well, any questions at all, folks, with any of those announcements? Okay, next, I'd like to turn it over to everyone in the class. Any questions that folks would like to discuss about exam 3?
I have one that I wouldn't mind going over.
Absolutely.
One time that I was able to fight yet. I think it's not if you want.
Yeah, let me pull up a new document. And since we're kind of in an impromptu review mode for the exam, which we discussed we're absolutely willing to do, it's a good idea. I'm going to put anything that we solve on this document too. Let me actually save it right now. Let's call it, should have opened this document before I got started today, but here we are, we're getting it figured out. I'll call this exam 3 class review. And where I'll publish it, it'll be right on top here. So that's where it's going to end up. So how did the question go on that one?
It's just f of x equals x power 2 over x to the power 2 plus 3. Isn't what that is full, but
Yeah, these things get kind of wild. What was the question they were asking about on this one?
Is to find the maximum and minimum height.
Gotcha. So let's see what we can do on this one. So first, this is a really good review question because out of the gate, the first derivative looks like it could be annoying. We need to hit it with the quotient rule. So let's start by going f prime at x. First, differentiate that x squared to produce a 2x. And then it has to be multiplied by the full denominator, x squared plus 3. And let's maybe go a little bit slower. I mean, this is an exam review question. There's no reason to do this as fast as possible. So let me color code the results as I do. I'll put the color coding in to signify we took a derivative there. And no color coding means we just copied it in. Next, we'll have a minus, copy an x squared, but then differentiate x squared plus 3. That's going to give us a times 2x here as well. Let me just fix that, make it look a little bit similar. Then the full thing is divided by x squared plus 3 squared. So that's our setup to start. Next thing we're doing is simplifying it as much as feasibly algebraically possible, since we're going to have to equation solve. So here to here will give us 2x cubed. Here to here will just be a plus 6x. That's kind of nice since these two combine to a 2x cubed as well with a negative sign. Denominator is going to be x squared plus 3 squared. And now we've got an elimination of the 2x cubed, 2x cubed. So I'll just write it equals here just to clean it up a little bit more. We have 6x divided by x squared plus 3 power 2. It's now set to 0 to get our critical number. And immediately all that happens is you set the numerator to 0. So this will imply 6x equals 0 right away. That's a pretty common step since all you're really doing is a cross product. You're multiplying both sides by x squared plus 3 squared to clear that denominator. And thanks to the 0, it's just wiped out. So that means there's only one solution, x equals 0. Oops, let me use the more official color. This implies x equals 0 is the critical number. Of f. Now we have to be a little bit paranoid the moment we find a critical number and we're looking at a fraction like this, because critical numbers can also occur wherever the derivative just fails to exist. And that's common whenever we have a point here that's not in the domain. But thankfully, because of the power 2, this is a positive quantity, plus 3. That means the denominator is never 0. So this would really be the only critical number that we could pick up. So once we find that, we'll throw in the number line. 0 is produced here. We'll go from negative infinity, positive infinity. And the next step is to check out what happens in this interval and this interval. So we're using test values. But usually you want to make the critical number kind of pop out because that's what's going to divide up intervals of increase versus decrease. So if you're working at just a pencil, just put a really light mark so it doesn't stand out as much. We'll test at -1, that's a natural number to throw in. Test at +1. So first with that -1, we're going to be evaluating f prime -1. This is where it's a pretty good idea to try to be, well, it's like bookkeeping. You want to put all these symbols to indicate your derivative, just so that we don't get mixed up with the original function, the first derivative, potentially the second derivative could be on the table. So f prime of -1 means we're plugging it in here. Denominator is always positive. I mean, x squared with the -1 is positive, but that power 2 forces it positive as well. So we know that this is going to be 6 by -1, -1 squared plus 3 squared. That's just a negative quantity right at this stage, thanks to the numerator. So back on the interval where we tested that value, we'll say here, the first derivative, so f prime, usually we just leave f prime as one overall symbol. I was about to put f prime at x, but that's a stylistic choice. No harm in doing that either. Let's leave it in that way. So f prime of x is negative here always, no matter what. That means I'm anticipating positive here, but that's always good to double check. Let's write it in, f prime of x positive, but then actually check it out. Let's put 1 inside that function. So we have f prime at 1 is 6 times 1 divided by 1 squared plus 3 squared. Everything there's positive, so we'll just say, yeah, we were right. F prime is positive in that region. So next thing, we can now say that the derivative represents the slope of the tangent line at all values. So if we're saying f prime is always negative here, That means the tangent line is slanting this way, and the function is always decreasing in that range. Likewise, positive derivative here means the function is increasing. And we're referring to the original function way up here when we say decreasing, increasing. You know, it might not be a bad idea to emphasize that by putting f here and here, but the downside is you don't want to make the diagram too busy, so try not to throw in too much stuff. So once we have that, we know that, just to paraphrase, f is decreasing. On negative infinity up to 0, and is increasing on zero to positive infinity. And now we can make an overall conclusion. There's one critical number, so there's only one local extreme value. We don't know the exact plot of the function. We'd have to do a lot more work to produce it. But when you see, write out these sign charts, here's a thought a lot of people kind of have in the back of their mind. I'll delete this in a moment so the diagram doesn't get too busy. But whatever the graph of this curve is, starts off decreasing. So let me just draw something decreasing. Here, that was a critical number, so the tangent line should be horizontal. Then it goes off and begins to increase. So there it is, increasing. And that means down here, we have a local minimum. So we just need to say that as an overall conclusion. F at 0, which means we're putting 0 not in the first derivative. We're going all the way back up to the original function. Throw a 0 in there and we'll get 0. Divide by 0 squared plus 3. And this could be undefined, but if the denominator is non-zero, 0 divided by 3 is just fine. It's 0 over 0 we'd have to worry about. But this whole thing is just 0 in totality. And that value of 0 is a local min for the function. We did it, folks. These are sometimes pretty tricky problems to get through. But any questions on getting to that end conclusion? Okay, so that's one down. Other questions that folks would like to discuss today? Yeah.
So when is 0, when you equal 0, when is that about? I remember you mentioned that somewhere earlier.
Let me see here. Let me think about that. Do you remember kind of what the context was?
Critical number is 0. What that means. What that means.
I might have been thinking along the lines of, let me know if this seems a little bit off, but sometimes when you get a critical number of 0, the thing that's kind of tough about that is 0 is usually your natural choice for a test value, but it's now been eliminated. I think back in the day where that could have come up, that might have been 4.2. Let me see here.
Yeah, 4.2 is just about the, how can you undefined? Okay.
You know, this one would have been awkward on example 3, having a 0 right here. Oh, I see what you're saying. On this particular example 3, 0 was not in the domain of the original function x. And so we had to start the domain right at 0. That means 0 is not a critical number at all. And it made it awkward because our test value was somewhere out here. So if you have something like this, that the 0 was playing a different role, that was the end boundary of the domain. And right at the boundary of the domain, we don't have local minimums, local maximums whatsoever. Could be absolute minimums or absolute maximums. But does that seem kind of close to the concept you were talking about? Gotcha. So usually 0 is a critical number. It is inconvenient since you'd like to use 0 as a test value, but you're prohibited right here. I'd say the larger issue is watch out for odd domain conditions like this one. What other questions, folks, about this problem or other problems you'd like to take a look at? Okay, Well, we're gonna go back to section, where are we? 4.6. I did want to mention if something just pops up and you're thinking, oh yeah, I want to take a look at that problem, don't hesitate to interject. I realize exam 3 is next Monday, but for the moment, I'm gonna save these notes here. And I will upload them to this location, right above the 3 exam material PDFs that you see right there, is where the class review questions will go. And for the moment, we're going now to section 4.6, back to antiderivatives. I felt like before just jumping into part C on this one, that doesn't seem very nice, might be a good idea to do a few warm-up problems. So here are those warm-up problems. I have 3 different functions. They're written in as lowercase. That means we're trying to find an antiderivative, which would be typically written as uppercase. And then this whole set of notes, I'm using blue to denote antiderivative for this kind of context. So let's review how this ought to go. If you have a power function, differentiating this is not too bad. 8 would come down and multiply, so you get 24, x to the power of 1 less 7. But if you're producing an antiderivative, it's a whole new game. You leave the 3 right where it is, go to the variable x, and this doesn't go down, it increases in power. And that's actually the first thing we do. We're not dividing by 8. We're going to raise the power to 9. Then we have to divide by 9. And that's also not the whole story. We're looking for the most general antiderivative possible. So we put in a plus c, an arbitrary constant. So that could be 0, it could be square root of 2, it could be 10 billion, or 3, just any number. We still have to simplify these things. So this would have to be simplified to 1/3. And that would be our antiderivative. F of x is 1/3 x to the power of 9 plus a constant. And the important concept about all of these is we shouldn't be totally satisfied once you find an antiderivative, although that is the answer. If that's all you gave me on a quiz problem, exam problem, I am okay with that. I'll just assume that you did this as a mental check. And it would go about like this. Take your answer, differentiate it immediately. If you did that, 9 is going to come down, multiply 1/3, so we have 9/3. The new power next goes down now, so it's a power 8. This is a fancy constant, but it is still just a constant. It's not related to any variable x, so it vanishes. And you could do more and more algebra here, but it is just a check. 9/3 does simplify down to 3. So that means we're looking at 3x cubed immediately. So I would call it just f of x. I put a check there to tell myself, that looks like the right antiderivative. We've got it at that stage. So that was the major kind of stuff we did at the end of Monday's class in this section. Any questions at all, folks, with that warm-up problem there? Okay, let's try this out again. Now, the one in the middle pane is probably, I'd say, one of the nastier kind of trick questions that could ever show up on an exam. The reason it's a trick question is this process doesn't work at all. If you try to use that process, let me put here just as a warning, don't copy. And I misspelled it at the same time. Let me see if I can fix this. Don't copy, this is wrong. Let's just put that there for a moment, just so if anyone's peeking in class, they'll know that we're doing a misadventure here. But imagine you saw that function and you're trying to do the same process as what you saw on the left. You would have written, first let me bring in the function. You would have probably written f of x equals 9. Now, once we carry in the constant, we go to the base x. And we don't divide by -1. We have to increase the power by 1 first before we divide. So if we did that, you get power 0. You have to divide by that new power, whatever it is. And there's your problem. Suddenly, this whole thing is undefined. I'll just abbreviate as UND for undefined. That means this is the exceptional one that we made a really big deal out of last class. That one doesn't obey the power rule when you're finding the antiderivative. You actually get a logarithm out of that. It's a total surprise. So math gets weird with this kind of stuff. So watch out for this. It's really hard to spot them sometimes that you run into that issue. Let me eliminate this incorrect math. And this is what I would encourage you to do as a very first step. When you see something to a power of -1 and you're finding an antiderivative, instead call the function f of x equals 9 times 1 over x. And notice we almost would never do that. Usually if we're going to differentiate something, we've always said you want to bring the base x up into the numerator so you can use a power rule in the normal way. But now that we're doing antiderivatives, this is the one case it just doesn't work. The formula that goes along with this is now finally, antiderivative f of x will be 9 times antiderivative of 1 over x is the natural logarithm of the absolute value of x, and then we throw in a constant c. So I would say this is one of the more tricky kind of questions ever to always watch out for in a calculus class. So let's check it out by differentiation. F prime of x will be equal to 9 times. Now we know the derivative of log x, natural log x, is 1 over x. And the next surprise that we discussed in section 3.7, this is right before spring break, so I know it was a while, but even if you differentiate natural log of absolute value of x, it is still 1 over x. Then this constant here will go to 0. And at this stage, 9 times 1 over x, that's exactly what we were looking at right here. So we can call it f of x, and our check is complete. Any questions, folks, with that middle example there? Okay, definitely watch out for it. I think it's rude to put that on an exam, but it could happen. Maybe not necessarily in this class, but other work that you do. Watch out for that one. Usually when I try to write an exam question, I'm not trying to put it in the most confusing format. This is a little bit more normal to look at. But even that, it could be a little bit weird. A real exam question could be like this. F of x is 9 over x. And suddenly it's a little bit harder to identify. If you see x in the denominator of power 1, immediately write it like this, and it will reveal that, oh, you're just going to get a natural log of absolute value of x. Pattern is a little bit more clear in this format. Well, that's a lot to say in the middle one, but that's because it's a tricky one. Now let's move on to this one right here. E to the x. Any volunteers for what the antiderivative should be for this one? Exactly, this is the nice one. The derivative, it's always the same, and an antidifferentiation, always the same. This is one I would probably not even check it, because, I mean, you could just eyeball it. Derivative of e to the x is itself, so that goes and checks out. Derivative of a constant goes to 0, and so we absolutely have the right thing the moment we write it down. Well, that's 3 fast problems. Any questions, folks, with getting through either one? Okay, now with all that said, here's where it gets kind of ugly. We need to find the antiderivative of this thing. Here's our part C to our next problem we're going to do. And it's not going to work if we try to find the antiderivative of 3x, negative 3x all on its own. We also can't just find antiderivative of x plus 5 all on its own, and so on. And we should expect that, because if we were differentiating this, that strategy also doesn't work. You'd have to use a 3-sided product rule, but the better strategy would just be to expand all of this and differentiate term by term. For antiderivatives, same exact strategy. We're going to expand it all, simplify it, and just go term by term, finding antiderivatives. So first step, let's say f of x equals, I'll leave the negative 3x right where it is, right here. And then I want to expand out this portion. So first, distribute the x into the group to the right, and you'll get 3x squared minus x. Distribute 5 into that same group to the right, and we'll get plus 15x minus 5. So distribution's complete. It goes plus natural log 4. It's pretty well expanded. Let's combine terms in the middle. We have 3x squared plus 14x's minus 5 plus natural logarithm 4. The final thing we've got to do is just distribute the negative 3x into that group to the right. So we'll have now negative 9x cubed, 3 by 14. That sounds like a negative 42. Let me know if my numbers go sideways. 3 by 4 is 12. Yeah, that sounds about right. That -3 times -5 will give us altogether positive 15x's plus natural logarithm 4. So that's our f of x function, following the qualities all the way down. We just want the antiderivative of that whole thing. So that means we're going to blue. This will be our answer. First thing we'll do is use the constant multiple rule. -9 is multiplying, so we just draw it in. Go over to your base x. The new power is always 1 higher if you're defining the antiderivative. So now it's to the power 4, which means we divide by that new power. And the coefficient's now -9/4. So that's pretty much the pattern for every single one of these. Kind of nice in a way. We'll go term by term. Next one is -42 to start. Then we look at x squared and write it in as x, but now to the power 3. The moment you've produced a power 3, divide by that new exponent. So 2 down, rinse and repeat. Any volunteers for what the result should be for 15x? Anyone in Zoom happen to see what ought to go right here?
Is it x squared?
Exactly. We'll have x squared for the new power on x, which means that new power of 2 has to divide the 15 right here. So we'll have 15 halves x squared. So yeah, we're on our track, the right track with this one. And I think now that we get to this stage, this is probably the hardest part of the whole problem. It just looks weird. But that's a constant for sure. And a related problem could have looked like this. If you had y equals, not natural log 4, but just say 4, that's a much easier constant to deal with. Then the antiderivative of that would be f of x equals 4x plus a constant. Reason for that is if you differentiate 4x, you do get 4 right back. So that proves we have the right answer. This constant will go to a 0. And it's the same pattern over here. It just kind of hurts our eyes to look at it. It's an awkward constant. But natural log 4, let's take a look at it. Seeing is believing. So somehow putting in the calculator like this just to exhibit it's a true constant, that actually helps. That's kind of weird how the mind works. So because it's constant, we can say from plus natural log 4, you would get plus natural log 4 again times x. Much like how we put the x right here on the simpler example for analogy. That's confusing enough. We'll use the yellow highlighting here to just convey how we got to that result. And finding the one thing that I practically have an inner mantra that I remind myself of, don't forget the arbitrary constant. I've lost serious points as a calculus student for forgetting that one little letter. It actually really is important. The more calculus you take, you realize forgetting that can really screw up a lot of mathematics, and it could be hard to know why. But any questions at all, folks, with that answer there? If we fed this to WebAssign, we might be okay, but sometimes WebAssign would complain because that simplifies. We do know that when we took the 3 times 14, that's how we got the 42. So dividing by 3, we're just back to 14. It'll be a -14. It's kind of unfortunate to recopy this whole line to get a small simplification like that. But let's do it anyways. So -9x power 4 minus 14x cubed plus 15 halves x squared plus natural logarithm of 4 times x plus a constant. So that's our end answer on this problem. We're definitely not done with it because, again, I encourage you, even if you're doing it mentally, by mentally I mean differentiate that, either way you do it, you should still always check these out. Differentiation is easier than antiderivatives, and we have a lot of practice dealing with differentiation from chapter 3, so leverage that to your advantage. It helps out on a massive degree. If you're eyeballing it, that's a fine way to check it. Derivative of this, 4 would come down, wipe out that 4, and you just get -9 x cubed. That's what we have right here. Notice our check is not to get back to this. You'd have to do additional algebra. Our check is to get back to this line where we are ready to go in antiderivative. But let's do it this way so it shows up on the paper better instead of eyeballing it. My check would be on paper usually something like this. F prime of x. Now we will get -9/4 times 4, because in differentiation, the first thing that happens is 4 multiplies. Then the next thing that happens is we drop the power. It's now power 3. So next, 3 times -14 will give us the -42. X to the power of 1 less, it's now power 2. Here we had 15/2. But then differentiation, 2 comes down, and power of x is 1. This one is differentiating a constant times a power 1 function, so you just take the constant. And the derivative here goes to 0. Let's check out what we have. So notice that a lot of this stuff is just sort of lined up. The 4's cancel, we get -9x cubed. We have -42x squared. Here, the 2's cancel. You get 15x. We have the natural log 4, and so this tells us that, yep, we have f of x, so the check is complete. Well, that's kind of a nasty one, I'd say, and a lot of problems in WebAssign kind of go like this. There's extra algebra you have to do just to start it up. This one was all about just expanding things out, but if you see a really weird one on WebAssign, come back to these notes because I have a couple weird ones too, like this is just a mess. A lot of work had to happen here. And this one we had to divide by x to clean it up, but pretty similar to the part C we just did. Well, any questions whatsoever, folks, with these kinds of questions? Okay, well, we're ready for a couple applications. This first application is purely a mathematical one. It says solve for a function. The equation that we're dealing with involves a derivative. This one's a second derivative. And so this would be referred to as a second order differential equation. And we've been fighting differential equations already. Our big application section in chapter 3, I forget the section, maybe 3.6, was all about solving a differential equation so we could model exponential growth, exponential decay. That was a first order differential equation. This one's second order because there's a second derivative here. Differential equations is a pretty vast subject, but it's kind of cool that we start to see what we mean by it just already in this calculus class. These problems are a little bit different. My color coding isn't going to work exactly, but I'll try to bring in my end answer and it's blue. So we have f double prime of x equals all this stuff right here. We want to solve for the function f. And the first thing we do is, if you see the second derivative, you're going down to the first derivative, f prime of x. Now, that means you're taking an antiderivative. That means our same methods for what we did before do apply to this. We'll copy in 15, throw in the base x, but bump its power now up to 3, 1 higher. After exhibiting the new exponent, divide by it. And then same step right here. This one is just like the natural log 4. E is a constant, and so when you find an antiderivative of this one, you go minus e, and then multiply by x. And I look at that, that always looks weird to my mind. We're used to writing out e to the x as an exponential function. That's different. That's just e times x. That's a linear function now with a slope e. So watch out for that. The way you write these down can potentially cause confusion. Now, there is still one thing missing. Anyone see what the last portion ought to be? Good call. We're still finding an antiderivative, and so we still need an arbitrary constant. So plus c on this one. Well, once we have that, it said solve for the function f, and we're not there yet. We got to, well, the first derivative. We need to peel back another derivative here to get back to f of x. We won't call this one uppercase f of x. We'll just call it a lowercase. I still want to use blue to convey that our end answer is now this second order antiderivative. We found antiderivatives twice, in other words. And I might be jumping the gun a little bit on this. Looking at my algebra again, it's always a good call to simplify before dropping to the next step. So let's see if I can squeeze that in. There we go. So f prime of x was 5x cubed minus e times x plus a constant. These are usually uppercase, but that's not super important. So if you wrote it as a lowercase, you're making a stylistic choice, which is totally fine. All right, back on track. Always a good idea to simplify. It actually can make these really confusing if you're dealing with just crazy constants, not simplified. So this one will finally turn into copy the coefficient of 5 to start. X is to the power 1 higher 4. Divide by that new higher power, 4, to get 5/4. And over here, it looks weird, but we just do it again. Minus e. Imagine it's just another number like 3. X is to power 1 here, so now it's bumped up to power 2. So you divide by 2 in this spot. Now, this is something new for sure. That's an arbitrary constant. And if you find an antiderivative of that thing, you take c times x. There's still something missing. Every time you find an antiderivative, you get a brand new arbitrary constant. And we can't put c here again because that would convey whatever goes here is the same as this constant. So usually we just go to the next letter of the alphabet. But if you run out of letters, people might call it C1, C2 for their constants to tell them apart. So you're welcome to use subscripting if that looks like a better approach. On the notes, I typically just go to the next letter in the alphabet, D. So there it is, folks. This is our total original function f. We had to find 2 antiderivatives to get there, which means 2 arbitrary constants. If we found an antiderivative again, we'd have even more constants. This would have been c squared, or excuse me, c divided by 2x squared and so on. But any questions, folks, at the moment? Okay, I do want to talk about one idea which is really interesting and kind of confusing. Let's put here, just as an emphasis, C and D are arbitrary constants. We say that all the time, that C is an arbitrary constant, but we don't always convey very well what we mean. It means C and D can take on any real number whatsoever. That's part of the reason I couldn't put a C right there, because now I'm saying whatever number C takes, this number has to take. But they could be different real numbers. Any pair of real numbers can now be used. And here's the weird part then. Suppose you had a function. Let me put a border here to say our problem is done. But suppose you had a function f of x equals cx plus d, and you want to take yet another antiderivative of that function. Here's one way it could be written in. F of x would be copying the constant c. New power of x is x squared. And then you would divide c by 2, but do you really need to? Here's the weird thing. If c is arbitrary, it can be any real number. C over 2 is also arbitrary. That's also literally any real number. And so if you left your answer like this, it is just as correct as writing in C over 2. But does that make sense to folks? Okay, so if C takes out any value, so does C over 2. For that reason, we sometimes just leave it in that format. Really kind of weird. This one would turn into d times x. We would need a new arbitrary constant e. And this would be the right antiderivative. I shouldn't leave the notes in this format. This is correct because, oh, not because of that. Let's see here, just so that there's a paper trail in the notes and we know why that's correct, because it really looks like a mistake. This is correct since C over two and C both represent any real number. So that's, again, some weird things that happen mathematically once you're dealing with solving differential equations by finding antiderivatives. So that deserves explanation. But any questions, folks, with solving that differential equation there? Okay, we'll skip the check all these since I think we are pretty well versed on how the check should go. Let's go off to the next problem, part B. Part B is also a differential equation. It's also second order because of the second derivative right here. But notice we have extra conditions on this thing. So sometimes when you're solving a differential equation, you want the total solution set, which is this, a family of functions indexed by an arbitrary real number here and an arbitrary real number here. That's a whole bunch of functions, infinitely many. But sometimes you want a specific function that satisfies conditions, like in this setup right here. So in this context, we would call this an initial, let me see if I can get this bracket put in a little bit better. This would be referred to as an initial value problem in differential equations. So that's a good naming scheme. It's called an initial value because these are the two initial values your answer has to satisfy no matter what. So on paper, this looks totally different from what we did before, but it's actually highly similar. The only thing that's new here is when we produce the constants, we're also going to solve to find their exact value. We're trying to drill down on one specific function, not infinitely many different ones on this new problem. And we'll hide example 3 as well. There we go. Any questions at all so far before we launch into this one? Okay, very, very similar ideas. So let's just go right for it. So on the second derivative, first thing we're going to do is just pull up f prime of x. That'll be our first antiderivative. It starts as 3x squared, so copy the constant 3. Go to x, its new power is 3. So that means you're going to divide by 3. But if you anticipated that this is going to become x cubed, so you're dividing by 3 and you didn't write anything down, good on you. That would say that you've done a lot of antiderivatives. That's kind of the goal, is to kind of look ahead and not even have to write the step. But when you're learning it, it is a good step to write in, just to be careful. So next thing, it's a -1, so that'll turn into -1 times x, which we can abbreviate to negative x. This was an antiderivative, so we put in c, the arbitrary constant. We cannot solve for c, unfortunately, because when we look at our initial values, that's not a derivative and neither is that. If this did have f prime at 0, then because this one is an f prime function, we could have used it to solve for c right away. But these are initial values to the original function, not the derivative. So we have to go another layer down before we even solve for the constant c. So take another antiderivative. Oh, and before going to f of x, I seem to forget this step a lot. You definitely want to simplify that just to clean it up a little. Let me write in that step. F prime of x is equal to x cubed minus x plus a constant. Okay, we're in better shape now. Now let's find our antiderivatives. There's no coefficient here. So what'll happen is put in a little bit of extra space, then write in x power 4. And we have to multiply by 1/4. I usually like to write it out this way, but if you wrote x power 4 over 4, and that way, just as good. It's just a different stylistic choice. So next one, we have a -1. I'll just throw in a negative sign to start. X, give it a little bit of space, is now up to power 2, so we have to divide by 2. So it's a -1/2 that goes in front. This step is confusing, but just follow that That's a constant, and so it has to obey this rule. Any constant in anti-differentiation, you just slap an X on it and call it good. So that's the right value there. The derivative of this goes back to C. And finally, one last constant, D, because we did a second antiderivative. Well, that's our almost answer. We next need to use these initial values, both of them, to solve for both constants, C and D. But this is most of the work so far, I'd say. It's the calculus work. Any questions at this stage? Okay, so between these two initial conditions, I don't like this one. This one's kind of annoying because when it says f of -1, you're plugging -1 here, here, and here. It's a bunch of a mess, and I can't even solve for anything. But that one is really nice. It's just going to clean up the algebra. It could have been f of 1 is 3, but then we have to solve a system of two linear equations. That's more like linear algebra. So usually there's a bit of a shortcut in some of these problems. Let's start with this one right here. F of 0 equals 3. First thing I would do is just say, what does that mean? We're referring to the original function f. And so we're plugging 0 into all these three positions where x exists. So it'll be an equation 1/4 times 0 minus 1/2 times 0 plus c times 0 plus d equals 3. Zeros are nice for this kind of setup. Everything's gone except for d, and so now we have d equals 3. So we need to update our function. And if you did this on your paper and just sort of erased it and threw a 3 in there, that's absolutely appropriate. I think a lot of people would do that. It might make your notes kind of confusing to read because your steps don't seem to necessarily have a linear order. And for that reason, I usually don't show that shortcut on the notes. It becomes really confusing to read the notes. Instead, I would usually just go like this. Update the f function. It's 1/4 x power 4 minus 1/2 x squared plus cx plus 3. So we solved for that constant there. Well, that was so fun. We just rinse and repeat. We're going to go over to this value and do the same thing. It's still going to be annoying because we have fractions, but now when we put in -1, there's only one unknown, just c. We're not solving for both c and d with a single equation. So write in f -1 equals 10. So we're done with that information there. -1 is going to plug into your f of x function. And so this will turn into, well, -1 to the power 4 is a positive one. So this will be just 1/4 minus 1/2. Put a -1 here. If it's power 2, that's also a positive one. So that's just going to be -1/2. Here we do have a change. This is -1 times c. I'll write it in as -c plus 3 equals to 10. So it's still an annoying equation, but it's definitely manageable. We can multiply this by 2/2. So now it's 1/4 minus 2/4. Let's also subtract 3 from both sides so we don't have to look at it. So left to right, 1/4 minus 2/4 is -1/4 minus c equals, also subtract 3 from both sides, and now we have a 7, but we're going to add 1/4 to both sides. So let's take this 7 and convert it to 4 in the denominator, 28 in the numerator. So multiplying by 4/4, 28/4 goes back to 7, so we're on the right track. Now add 1/4 to that. -c is now equal to 29/4. Almost there. Now multiply both sides by -1. C equals -29/4. And we're still not done, but again, no judgment at all. If you just erase that and throw -29/4 there, you're saving a little bit of copying. But for me, I would like to have a nice paper trail in the notes, so let's write in this last step. F of x equals 1/4 x to the power 4 minus 1/2 x squared. C came out as -29/4. So from right here, let's write in -29/4 x plus 3. And I want to definitely box this one out because there's algebra everywhere. That's finally our total answer right at that stage. Let's see if we can zoom out to the right level here. Well, we did it, folks. That's the full process of solving an initial value problem. When you solve a lot of these, you might start to you may not like them a lot because it comes with a lot of algebra that is a little bit tedious some of the times. But if this was an exam question, I do throw in some zeros so you can speed through a lot of it. If this was a real exam question, I'd probably put a 0 in right here as well. So it's more about the calculus, less about getting bogged down in algebra. But any questions at all, folks, on running through this one? Okay, well, let's take a look at the last problem. This one is our honest application for this section. Everything were applications above, but that was applications to differential equations. It doesn't feel like a very exciting one if it's a math-specific application. This one feels kind of mathy because I don't have any interesting context, but you can imagine there could absolutely be some interesting context to this. It says a particle is moving with the given data. So just a reminder that in a calculus class, as opposed to physics, we're only moving in one single dimension. So you can imagine a particle in a Large Hadron Collider, or you can just imagine, say, an object that's moving like this. Maybe it's a projectile, so you launch something and it's moving that way. We're only tracking the height. So this would give a y-axis. And this is where all the calculus is going to live, how the thing changes on its height, not its two-dimensional trajectory. So we're analyzing one dimensions at a time. So this is all we know about it, is that the particle moves. Maybe it's something like a car. We're just tracking the distance from a starting point. We want to find the position of the particle at time t. Let's put that in blue because we have to take antiderivatives, and that's going to be the end answer on that one. It's also an initial value problem. We have an initial position, an initial velocity, and we have to start with information about acceleration. Well, it's not always easy to see where to start these kinds of problems, but this is how we would probably think about it. Let's organize by recalling some information way back in chapter 3. If you write out s of t, that's kind of a weird variable, but physicists, I believe, like to indicate a position function with s for some reason. So s is going to be the position at time t. Now we have v right here. This one's velocity, and we can write out this, v of t equals velocity at time t. But already knowing that that's velocity means it's a rate of change of position. So you can say over here to the right that this implies if you take the derivative of position, you get velocity. So that's interesting on its own. And now let's go one level down. We need to talk about this function. A at time t is the acceleration at time t. And I do want to pause right here. Acceleration is a tricky word because it's thought of as a physics word when we see it in a calculus setting. That means if I say acceleration, I don't mean goes faster. What we mean by acceleration is a change in velocity. If you were in a physics class, you would call acceleration either a change in velocity or a change in direction. So acceleration at time t just means you're either going faster or going slower. Your velocity is changing, is all it's mentioning. But from here, we can say something else as well. This implies if you take velocity, differentiate it, well, acceleration is just the rate of change of velocity, whether you're going faster or slower. So the derivative of velocity is acceleration at time t. So that's kind of interesting. That means if you want to find the position, You'd go here, given information is on acceleration, get to the antiderivative, velocity, find another antiderivative to get to the position function, the thing we're looking for. And because we have initial values, we can now track the position for all time, assuming this is always accurate for all time as well. But let's throw in one last thing. We have, just as an overall statement, S double prime at t is going to be equal to V prime at t. That's because if we put an extra prime right here on this equation, you're differentiating this one, so that's a V prime. But we also know V prime at t is acceleration at time t. So this is the organizing work. We now are going to start with acceleration at time t is -4 meters per second squared and move backwards by 1. We need an antiderivative for this, and that gives us velocity. So over here, that's a constant, so it's not a bad antiderivative. What makes this problem kind of challenging is we just need to know the names of these functions and how they relate to each other. That's actually the hardest part of the problem, I'd say. So velocity at time t is going to be -4 times t plus a constant. Now we have to find the position. And when it said the position, we're going for exactly one function here. That means we have to solve for this constant. And the last problem, we couldn't do that right away. We had to pull back and find another antiderivative. But this time we can, because they provided us a derivative right here. Velocity at time 1 is 10 meters per second. So we'll use that information right away and solve for the constant here now. If you can solve for the constant earlier, oftentimes that's the best algebraic step to take. So you're not doing this kind of stuff as much. So let's solve by saying, just recalling, v of 1 is 10. Where it says v of 1, that means you're just placing 1 right here for t. So -4 pi times 1 plus a constant is 10. We can just add 4 to both sides, and c is equal to 14. Then we come back over here, update the function. Velocity at time t is -4t plus 14. Well, that's one step down. Next thing we have to do is pull back again, one more antiderivative, and we will have position at time t. But first, any questions, folks, on getting to that stage? Okay, let's keep on going. Antiderivative right here, well, you know t is going to jump to a power 2, and then you would divide by 2. So if you've done lots of practice on here, it would be indicated by, you might write down -2t squared. But we're still learning this, so let's go methodically. Go -4. New power of t is 1 higher, so power 2. Then, and only then, divide by the new power. So it would look like that to start out. Working it methodically is a good idea when you're first learning this kind of stuff. So over here, let's do it again. That's just a constant, so we throw a variable at it, 14t. We need a new constant of integration. And because I used c here, I personally would use the next letter. If you did reuse c, that's not a big deal. I would just think of your new variable c is in a different scope than this one was. But I think this is a little bit cleaner to write, just change the variable. Once we did that, we go back up here. Here's the next most interesting initial value given. Position at time 0 is 1 meter. If it was a race, that would mean that this athlete has got a huge head start or is cheating 1 meter ahead of everyone else. So we'll say here, S of 0 is 1. And recall, those zeros are actually kind of nice. They get baked into a lot of problems, so we're not bogged down in so much algebra. What it means is, you're throwing a 0 here for t squared. That term's gone. This is 14 times 0, so that term's gone. It immediately just tells you d is 1, which means we have to update the function one last time. Let's write out position at time t. I guess we had to. We need to simplify this. It's -2t squared plus 14t plus Here's our last step, the constant D has to be a 1. So if anything moves in this kind of way, we now know where it's going to be located for all time. That's kind of interesting in a sense. It's definitely an interesting physics kind of problem, but any questions at all on getting through this one? Okay, well, we did it, folks. This is antiderivatives, section 4.6. It's a tricky section, but it's an extremely pivotal section because it turns out if you want to find the area under a curve, you need an antiderivative. And that is really kind of bizarre in a certain sense. That observation that getting areas under curves is referred to as the fundamental theorem of calculus. Well, at least one of its parts. Let's save up these notes. We have a good 14 minutes, so I don't think that's a good amount of time to make serious headway into section 5.1. Let me show you what it looks like. In section 5.1, our whole objective is to get that area. In this section, we're going to do this in a very, I don't like to use the word tedious, but I'm going to be honest. We're going to do it in a very tedious way. And there's an analogy here. We're going to find the area under the curve in the same way as we did this. In section 3.1, when we're finding derivatives and rates of change, we first, well, not quite what I was thinking, hang on. How about section, well, I think the better analogy might be this one. When we're trying to look at limits, we were first doing, oh, was it even this section? Maybe this one? Sorry, lost track of where everything was. This was quite a while ago. We've been through a lot. But we're going to start by doing it in this kind of way. This is the sort of analogy I was going for. This is not the best way to do math, but it has its purpose. It's a way to see what's going on under the hood when we were doing the limiting process, and that was something totally unfamiliar. We got a feel for what we meant about the limit emerging at 0. So we're going to do something kind of similar to this in this section. There are limits that are going to come up in section 5.1 to get this area. So if we took a preview of that, here's what it looks like. We need to chop up this interval into many different rectangles, then take the limit as the number of rectangles goes to infinity. It looks like that. It's kind of a mess. And that's going to give us the exact area under the curve. This is computing the really hard way, much like doing this right here. It's kind of tedious, but it gets us a feel for what's going to be really going on under the hood. But this is what we would really do once we have the fundamental theorem of calculus. Let's let this be our last concept for the notes. Once we have enough methods built up to actually find this area, this is all you really have to do. You consider this function right here. And it says that this curve, well, it's continuous. And that's enough. Every continuous function has an antiderivative, it turns out. So you would find this function. F of x is the antiderivative of that lowercase f of x. And now it turns out this area that's under the curve is simply the antiderivative evaluated at the upper value, b, minus the antiderivative evaluated at the lower endpoint, a, and that's an exact area. That doesn't even sound real, right? But this is the fundamental theorem of calculus. It was the observation by Isaac Newton and independently in German, Leibniz, that you can calculate like this. And the area under the curve only depends on the antiderivative on the boundary. Nothing in the middle matters. That's pretty bizarre. But to get to how this all works, we really have to chop up this interval here and start breaking down areas and seeing how it all goes. But I felt like after dealing so much with antiderivatives, it's a good idea to see why we care. We're trying to calculate areas. And an area can represent any physical quantity. It can be distance, time, energy, mass. Think of anything you're really interested in, it can be turned into an area problem, which means you're probably using antiderivatives if you're calculating complicated areas. But that's the preview of what we're getting into. We definitely don't have a lot of time to make any serious headway in 9 minutes, but any questions at the moment, folks? Okay, any last questions about the exam or other concepts folks would like to talk about? Okay, this will probably be a pretty good stopping point for us then. I just want to mention that as we're going towards our third exam, if you have any questions while you're studying these problems, please don't hesitate to write. I might not be available all weekend long, but I do check my email and I check it very habitually early in the morning. So even if you send me a question, say Friday at, well, let's say Saturday at 3 a.m., if you have a question, definitely write it down and just send it out. That way that question's fresh in your mind, and I'll just get to it when I see your email in the morning. But the reminder is that I would say these review problems right here are pretty decent ones. These ones out of the back of the book are just extra if you want to get extra practice, but they're from the online textbook, so they're still pretty good ones to take a look at. And your quizzes, every one of them relative to these sections, are also, I mean, they're meant to be great hints at what a real exam question would look like. I would definitely look at those again for studying. But I think I ran out of things I wanted to say. Have a great night, folks. Have a great weekend. And if you have any questions, don't hesitate to reach out. I'll be available to help.
Thank you.
Yep, absolutely.